Hi students, welcome back to Geology. Today we are going to learn about geochronology, which is the study of putting events, geologic events, into order. And so in order to study geochronology, we have to learn something about how rocks are dated, how we learn how old the rocks are, and how we put events in a sequence or an order. So just as a reminder, we are going to be looking at the geologic timescale and working with it throughout this unit. So remember that Earth is 4.6 billion years old, so we are going to have rocks dating back to very close to that time frame. The reason we don't have specifically 4.6 billion year old rocks is because they have been recycled. And so by the rock cycle, bringing them back down into the mantle and tectonics, we have lost some of those really, really old rocks. Just as a reminder, the geologic timescale is broken up into eons, eras, periods, and epochs, and we will be referencing some of these time frames throughout this unit. All right, how do we know how old rocks are? Well, we can use two different methods. The first is relative age dating. So relative age dating is a process by which we can put particular units or particular events that happened in Earth's past in order relative to one another. Okay, so for example, this unit is older than this unit because this unit is underneath this unit. That'll make more sense when we talk about the principles of geology, but for now, just know that relative age dating is putting things in order relative to another thing. Right? And then absolute age dating is where we actually use chemistry. So we're looking at radioactive elements that are unstable at Earth's surface and they decay over time. Based on known decay rates, we can calculate how long that rock has been sitting exposed at the surface or at not molten in the mantle. And from there, we can actually get a numeric date. So we can say that these rocks are 120 million years old rather than just saying that it's younger than the one underneath it. All right, so the first we're going to talk about is relative age dating. So again, this is where we determine relative order of events, and we're not necessarily getting an absolute age date here. So we cannot say, using this method, we cannot say that the rocks are 65 million years old or whatever we want to say. Okay, we can just say that it's older than something else or younger than something else. All right, so the first geologic principles that we are going to talk about are going to be both conceptual and geometric. So with geologic principles, we have the conceptuals, which are going to be just overall concepts that we are going to talk about. And then our geometric, we're going to look at physical interactions between rock layers and between units. Okay, so these geologic principles are going to help us figure out the relative ages of these rocks. Right, so first up are the conceptual principles. This first one is the principle of uniformitarianism. The principle of uniformitarianism says the present is the key to the past. So whatever we see in geology out on the open plains of the earth today is what we can use to assume what happened in the past. Okay, so whatever geologic processes that we're seeing right now, that gives us insight into what kind of geologic processes were in the past. With the principle of faunal succession, this is where we're looking at groups of fossils, plants, and animals, and we are using them to characterize a specific time frame. So, for example, trilobites, we know lived from the Cambrian to Permian time. So if you have a trilobite in the sample you're looking at, you will likely know that that rock formed sometime in the Cambrian to late Permian time because the specimen had to exist during that time. It couldn't be much older and it couldn't be younger, right? You needed the trilobite to die quickly and be covered with sediment quickly, so the age of the fossil and the sediment are likely around the same age. All right, moving on to our geometric principles. So this is where we're using physical relationships between layers of rock and events. Okay, so these are going to include the principle of original horizontality, the principle of superposition, the principle of cross-cutting relationships, age of inclusions, lateral continuity, and a few unconformities. So first things first, the principle of original horizontality says that most sedimentary rocks are deposited in a horizontal fashion. So rocks that you see that are horizontal like this are part of the original horizontality that the rocks were deposited in. If the rocks happen to be tilted at an angle, or maybe they're faulted or folded like we've seen with crustal deformation previously in this class, it's a possibility that they do not exhibit original horizontality and they have been altered after they were emplaced. Okay, so using original horizontality, you would know that whatever happened to them happened after they were deposited. All right, our next one is the principle of superposition. So in any given sedimentary sequence, the oldest rocks are on the bottom and the layers get younger upward. So, for example, we have a laundry basket here as an example. At the beginning of the week, you're going to throw your Monday clothes into your hamper. And at the bottom, they're going to land at the bottom, right? Hopefully, if you did your laundry that weekend. Tuesday, you're going to take your clothes off and you're going to put them on top of Monday's clothes. And then so on and so forth. And by the time you get to Friday, you have a full laundry basket and you do laundry again. Or maybe you wait until Sunday. Well, the clothes that are closest to the top are going to be the youngest, right? They were the most recently worn clothes. The ones at the bottom are going to be the oldest, okay? So it's the same thing with sediments. These shale deposits that are at the bottom there, that's going to be your oldest layer. And then the limestone would have showed up, and then the sandstone, and then looks like another shale, and then another sandstone layer. Okay, so you can tell the order in which these rocks were deposited by their relationship to one another and whether they are on the bottom, the middle, or the top. All right, and then we have the principle of cross-cutting relationships. This says that the cutter is younger than the cuttee. So whatever is cutting across layers and is penetrating through layers or affecting those layers, that layer is, or that whatever it is, it's a fault or it's a dike or an intrusion of some kind, that layer is younger than the layers it's cutting, because those layers 1 through 4 there in this diagram had to exist for that dike to cross through all of them. Okay, so they had to be emplaced first, and so they're all older than the dike is. Okay, so this is cross-cutting. So this is anything that crosses over layers. Then we have the age of inclusions. So in some rocks, we might see intrusions or inclusions, or sometimes they're referred to as xenoliths. And these xenoliths are rock fragments that are enveloped in a larger rock that was not necessarily associated with the larger rock's formation. And so that inclusion or that piece would be older than the overall rock that it exists in. So this example would be like a chocolate chip cookie. Right? You can't make a chocolate chip cookie if the chocolate chips don't already exist. So the chocolate chips exist, which are our xenoliths or our inclusions. And then you can make the cookie, which is the larger rock, which will be younger. The cookie is younger than the chocolate chips. All right, then we have lateral continuity, which is talking about sediments being deposited across a large area. So when rocks are deposited, sediments are deposited, we don't generally see them truncate really abruptly at the edges of those deposits, unless some other force is allowing that to happen. But in general, we have rocks that are spread out, the sediment spreads out, and it thins towards the edges. Okay, so if you see layers that are fully truncated in like a canyon, you can assume that the layers actually continue across that canyon. And so we call that lateral continuity, and we can match layers from one side of the canyon to the other. All right, and then the last thing here, we're going to look at unconformities. So unconformities are a gap in the rock record, and these can be characterized as nonconformities, disconformities, or angular unconformities. Okay, so the first one we're going to look at is a nonconformity. This is an unconformity in which there is a contact between an older igneous or metamorphic rock and it's overlain, or there is rocks on top of it that are sedimentary rocks specifically. And so this diagram on the left here shows you the emplacement of some sort of igneous body, right? That purple kind of color. And then there was an erosion that occurred. So a bunch of rocks were eroded down to that surface, and then more rocks deposited on top in time 3 there. And so that contact between those horizontal layers and that igneous rock that was emplaced many years before is a nonconformity. The way you can remember this one versus the other unconformities is that nonconformity, they don't conform. They're two different rock types. So if we have two different rock types here, we're looking at a nonconformity. Now with disconformity, it's a similar process, but we're working with only sedimentary rocks here. And so in time 1 here on the left, you see a bunch of sediments deposited, and then further erosion of those sediments. And then after that erosion, then you have more deposition of more sedimentary rocks, and that contact between the two is a disconformity. Now, what is the difference between just a contact or a bedding layer and an unconformity in this case? The difference is whether there was erosion that took place, significant erosion that took place between the rock layers. And so the rock layers will be significantly different ages, and they won't necessarily show a fairly uniform depositional sequence. When rocks are deposited one after another, and there's not a huge gap, we don't see a lot of erosion take place that is preserved in the rock record. And so these unconformities are those preserved erosional surfaces. Okay, and then the last one is an angular unconformity. So this occurs when rocks have been tilted or folded or squished in some manner, and then eventually all of those erode from the top as well. And then you have the erosional surface created, and then those rocks are overlain by more sedimentary layers. And so here it creates an angle difference between the horizontal layers on top and the tilted or folded layers at the bottom. And so this one's fairly easy to identify because if the layers are folded or at an angle versus the ones on top, then you automatically know you're looking at an angular unconformity. In general, this is going to be sedimentary deposits, just so you're aware. All right, so the next few slides, we're going to go through different sequences of geologic puzzles, and we are going to try to figure out what their sequence of events are based on the geologic principles we just learned. Okay, so each diagram is going to get progressively harder. So the first one's going to be an easy one, and then we'll do an intermediate, and then we'll do a much harder one. All right, so here's your beginner diagram A. So what do you think is the oldest layer here? Okay, the oldest layer is D. And the next oldest, C. Next oldest after that would be B. And then the youngest layer here is going to be A. Okay, so in your lab, you're going to be working with different diagrams like this, and you're going to be trying to put them in sequence of events just like this, but they're going to be a little bit harder. Okay, so this is our kind of beginner exercise. Now we're going to go into our intermediate. Okay, so here's our intermediate diagram. Take a second to look at it. I do recommend maybe trying in your notes first and then listening to the rest of the lecture. That way you can kind of get some practice. All right, so first things first, what is the oldest layer here? Okay, that would be F, right? So F down there at the bottom is the youngest layer, oldest layer, excuse me. Okay, and then what would be the next oldest layer? That would be E. Okay, so right now we're using superposition to stack up these layers. Just like we did in the first diagram, we used all superposition there. Okay, so that's what we're using first here to put in order some of these layers. Okay, so F happened first, then E, and then D, okay? And then what would be next? G, okay? So now we have F, E, D, and G. Those are all stacked on top of each other, right? If you can't see where G kind of interacts, you can see on the right-hand side of the diagram, G is directly above D, okay? So the next thing here, we could keep going with layers, but we also have some other things to consider. We have an erosional layer there, which is I. On these diagrams, for reference, these squiggly lines are usually erosional surfaces. And then anything that kind of transects as a line are faults. And you can kind of see that it looks like a fault because you see two layers that are offset. So H there is a fault and J is also a fault. So after G, what would have happened next? It should be H, right? So the fault, when it shifts those layers at the surface, you're going to have a couple of offset layers, but we don't see that. We see a nice smooth erosional surface. So the erosional surface would have happened after the actual faulting event. So there we have I. And then after the erosional surface, the next thing that would be deposited would be C. The next thing after that would be B. And then finally, our last layer would be A. And then the offset there of fault J would be our youngest layer. Okay, so hopefully that makes sense. Take your time. You can slow down the audio if you need to. Try to give yourself some practice. You'll practice more in lab, but like I said, this is not going to be an immediate, you get it really quickly, because sometimes it's like, oh, wait, what? Oh, okay. So don't be discouraged if this doesn't come to you right away, okay? It'll take some practice. All right, and here is our advanced diagram. So as you can tell, this diagram is a lot more complex than the other two. And so this is the type of diagram that you would work with in lab. You'd have one intermediate and one advanced, more than likely, or maybe a couple intermediate and a couple advanced, just so that you get to more opportunity to work with this material. Okay, so the first thing here is we need to figure out the oldest layer. Okay, so there's a couple of things that are hard to decide whether you're looking at B or D because they're not on top of each other necessarily. So the big thing here to consider is that there is a slice or a little inclusion of B within D. So that means that B must be older than D. Okay, so our oldest layer here is going to be B. Okay. Moving up, what would our next oldest layer be? That would be D, right? It's down there on the bottom. There's no reason to think that it's not. Okay, and then our next layer would be E, which is our fault. The reason we know that E comes before C or F is because the top there of D is fairly uniform. We don't see that offset that the fault would be creating. Remember, lines that transect through layers like that are faults. So we also have K on the left that is a fault as well. Okay, so after E, we have the erosional surface C. Okay. Then we have the deposition of F. Okay, so really quick, let me back up. With B to D, we used age of inclusions. With D, we used superposition. With E, we used cross-cutting relationships. And with C, we used unconformities. Now again, with F, we used superposition again. Okay. So then the next oldest layer would be I. I know that G is also interacting with I, but G is cutting through I, H, and M. Okay, so that means that all of those layers had to exist for G to cut through them. Okay, so after I, we would see the deposition of H, and then M, and then finally we would see G. So G is an intrusion of some kind or a dike that came through I and also through H and M. Then after G, we see the erosional surface J there on the top. It's in the blue, kind of in the center of the diagram there. So that squiggly line there, remember squiggly lines are erosional surfaces. And so that would be J. And then we have the deposition of A, which is the blue layer, the kind of brick-looking layer. That is A. And then next would be L. Okay, so right now we're just using superposition again. And then P. And then we get a little tricky, right? So we've got K, that's a fault. We have R and N that are erosional surfaces. We have some O thing there and a Q. Okay, so this is where it gets a little tricky. You got to pay attention. So, well, I mean, you have to pay attention the whole time, but you got to be a little more diligent. Okay, so with K, we see that it crosses through all of the layers, but then it stops right at the erosional surface R, which means that it must be our next layer. Okay, so K is our next layer after P, and then after that would be our erosional surface R, smooths everything out there. Okay, and then next we would see the deposition of Q. Okay, so Q is that top layer there. And so this is superposition again. And then these last two, we have the erosional surface first. So Q starts to get eroded, and then you have a canyon develop, right? So remember lateral continuity? So we have that canyon develop, and then O is deposited in the center of that stream or that canyon or whatever it is. Okay, so this is the sequence of events for diagram C. Okay, so it's really important to take this slow and really practice because you can get yourself kind of confused with the layers. And it's always good to try this first on a piece of paper before you submit anything online or try it in a quiz or anything like that. All right, so this was all relative age dating. We're going to move on to absolute age dating for the last part of this. Okay, so with absolute age dating, we are using radioactive decay and we are getting numerical dates. Okay, so we're actually being able to say this rock is 120 million years old instead of just saying it's older than this other rock over here. Okay. All right, so understanding radiometric dating, we need to know something about radioactivity. Okay, so this is when particular isotopes come to the surface in rocks. A lot of them aren't very stable at Earth's surface. So in a granite, for example, it usually contains a lot of uranium, but uranium isn't a very stable isotope at Earth's surface, and so it starts to decay to what we call lead. And so lead is the decay product of the uranium. And so we can relate those two isotopes to each other and their concentrations and be able to calculate the age based on known decay rates of uranium. Okay, so uranium would be what we call a parent atom or parent isotope, and the lead would be a daughter product or daughter isotope. Okay, so the daughter products are the decay products from the original isotope, which would be the parent isotope. Okay, so we will use their relationship to actually discuss how old things are. All right, so looking at radioactive decay, there's lots of different ways that radioactive decay can happen, but we have three basic types that we will talk about. The first is an alpha decay. And so this happens when an alpha particle, which consists of 2 protons and 2 neutrons, are emitted from the nucleus of an atom. Okay, and so the product 1 there, the unstable parent nucleus on the left under A alpha emission, will decay when 2 protons and 2 neutrons are emitted from or kicked out basically from that nucleus, and it becomes an entirely different isotope. Okay. The second way this can happen is through beta decay or beta emission, which is time B there in that diagram. So this happens when a neutron and its nucleus splits into an electron and a proton. And so you see the emission of that from the nucleus. And so your unstable parent atom became this more stable daughter product by the emission of an electron and a proton. Okay, and the last way is through electron capture. And this happens when a proton in the nucleus captures an electron from one of the electron shells and becomes a neutron. Okay, let me say that again. This is when a proton in the nucleus captures an electron from one of the electron shells. So remember, the electron shells are the outer shells of a nucleus, and it becomes a neutron. Okay, so there's a conversion there. And when that happens, it becomes more stable. Okay, so all of these radioactive decay methods are ways for the isotope to try to become more stable at the Earth's atmosphere, at the Earth's surface. Okay, so as this happens, there are certain isotopes that will decay faster than other isotopes. And the way that we measure that decay is by half-lives. Okay, so a half-life is the amount of time it takes for a radioactive isotope to lose half of its atoms. Okay, so we are losing half of the atoms to daughter product every half-life. Okay, and so, for example, here at 0 half-lives, we have 100% parent atoms. Okay, or 100% of it is the parent isotope. After 1 half-life, we've lost 50% of those parent atoms to daughter product. So now it's 50-50 in the sample. After 2 half-lives, we've lost an additional 50% of the parent atoms. So now we're at 25% parent and 75% daughter. If you look at the diagram here, it explains that a little bit in a visual capacity, where at time 0 with no half-lives, we have 100% parent at the top there. And as you move towards more half-lives, you can see that it asymptotically approaches 0, right? Because we are only losing half of the isotopes every half-life, you will never actually see 0 parent atoms, but you will see a very, very small fraction of the parent atoms left. And so there might be a very tiny concentration of uranium left in a very, very old granite. Okay, so some of the methods that we'll talk about when you do some examples here in a second will be determining how old, you will use to determine how old different rocks are. And a lot of them have really, really long half-lives, and so you need really old rocks. But what about things that we want to date that are not so old, like anything human related? Right, so the good news is we do have something called carbon-14 dating, and it only has a half-life of about 5,730 years. So we can use this to date really recent events and things that contain carbon. So any kind of plants or animals that have decayed into our soil, we can use those to help date how old those specimens are. So when we find really, really old humans, we can use carbon-14 dating to help us date how old that human is. All right, so here are some examples of calculating radioactivity. So we're given all of these different things. Suppose there are 500 atoms of radon-222. We have a chart down here that tells you the half-life for whatever radioactive substance we're talking about. After 8 days, how many parent atoms are left? So you can run that calculation. I'll give you the answers on the next slide. Suppose there are 1,000 atoms of pluton-239. After 72,360 years, how many parent atoms are left? How many daughter atoms are produced? Okay. And then suppose a particular sample has 25 parent atoms and 375 daughter atoms. How many half-lives has the sample experienced, and how many parent atoms were originally in the sample? Okay. I'll take a second to see if you can figure any of those out. And here are your answers. So suppose you have 500 atoms of radon-222. After 8 days, how many parent atoms are left? So radon-222 has a half-life of 4 days. So if there's 4 days for a half-life and it's gone through 8 days, that means that it has gone through So it's gone through 2 half-lives, and I have the wrong answer here, so make sure you're listening. It's gone through 2 half-lives, right? So 500 divided by 2 divided by 2. Okay, so we're looking at 125 parent atoms left. Okay, so ignore this answer. It's 125 parent atoms. Okay, so keep that in mind. You're looking at 4 days for a half-life. After 8 days, we've gone through 2 half-lives. So you need to divide by half or by 2 twice. Okay? Looking at number 2, suppose there are 1,000 atoms of pluton-239. After 72,360 years, how many parent atoms are left? How many daughter atoms are produced? 125 parent atoms and 875 daughter atoms. Okay? So how do we figure that out? So pluton-239 has a half-life of 24,120 years. So that is 3 half-lives if it's gone through 72,360 years. Okay, so that's 3 half-lives. So we need to take 1,000 atoms and divide by 2 3 times. Okay, so that would be 1,000 divided by 2, which is 500. So that's 1 half-life. 500 divided by 2 is 250. That's 2 half-lives. And then 250 divided by 2 is 125. That's 3 half-lives. Okay? And then to figure out how many daughter atoms were produced, you just subtract 125 from 1,000 because you are not losing or gaining atoms. Okay, so your answer always has to equal the total number of atoms that were originally in the sample. Okay, so that takes us into number 3. Suppose you have 25 parent atoms and 375 daughter atoms. How many parent atoms were originally in the sample? That would be 400 because 25 plus 375 is 400. Remember, we're not gaining or losing atoms. Okay, and then we've got how many half-lives has a sample experienced? Well, you take 400, you keep dividing by 2 until you get to 25, and you get 4 half-lives. So 400 divided by 2 is 200. So that's 1 half-life. 200 divided by 2 is 100. It's 2 half-lives. 100 divided by 2 is 50. It's 3 half-lives. And then 50 divided by 2 is 25. That's 4 half-lives. And so we got to our 25 number. Okay. If you have any trouble with this, please email me. I know this is kind of hard to do virtually, but if you struggle, please see our tutor or come to me in my office hour or drop in if you still need some help with calculating some of these things. All right, combining dating methods, we can also use relative and absolute age dating together. Okay, so we can say that the layer at the bottom there is older than the layers at the top. And then we can also say that some of these layers that have fossils in them or they have rocks in them that we can actually date, and we can kind of put some numbers in between. And so, for example, a couple of the layers like the yellow layer at the top with the shells in it, we can say that it's somewhere between 510 million years and 495 million years, but we can't say specifically that it's 500 million years because we can't date that layer. So we can say that it's bracketed between those based on the layers that we could date radiometrically. But this is how you would use those two together. Okay, so rocks are dated in 2 ways. We talked about relative and absolute age dating. Relative dating uses rock layers and looking at them, their physical contact with each other and putting them in a sequence of events. Absolute age dating uses radioactive elements, half-lives, and gives us a numeric date. And we can use both in combination together to figure out how rocks were placed in a specific area. All right, I'll see you guys in the next video. Bye.